Today I want to test my self-made 3D printed ATC ventilator. The ventilator is connected via a 7mm endotracheal tube and an artificial trachea to a lung simulator. This is the user interface for the ventilator. This is the lung simulator. And we also want to compare our ventilator with a commercial Dräger V600 ventilator. This is now the screenshot from our lung simulator. The top panel shows the tracheal pressure in blue, airway pressure in orange. The middle panel, the flow pattern. It's a sinusoidal flow with a peak of 1 liter per second in inspiration and expiration. As you can see, the tracheal pressure is close to the target pressure, so it's close to the peak value of 0 in this case, and the airway pressure increases in inspiration to about 10 or 11 centimeters. And in expiration decreases to about the same value. And note the root mean square tracheal pressure, which is the effective resistance, so it's 1.8 millibar per liter and second. And so now what you just saw is we switched to a T-piece trial. So we disconnected the ventilator and now the airway pressure is constant and the tracheal pressure in inspiration decreases by this 10 centimeters of water and increase in expiration by about the same amount. And now you see the effective resistance is 10.9 millibar per liter and second. What we are now doing is we are connecting our lung simulator to our Dräger V600 ventilator in ATC mode. PEEP is 5. And as you will notice, the ventilator needs a few seconds to adjust its control parameters. So the tracheal pressure is supposed to be on this blue dotted line. So it should be constant. It is not. Airway pressure increase in inspiration and the ventilator tries to decrease, but it can't decrease it below 0. And so we see that the tracheal pressure increases also in expiration. And the effective resistance as expressed by the standard deviation of the tracheal pressure divided by the standard deviation of the flow. That's the RMS tracheal pressure, and that's the effective resistance. So it's 6.7 millibar per liter and second. So it decreased from 10.9 in T-piece trial to 6.8. But as you can see, it's not really in a very effective mode. So that's only about 40% of tube compensation. And there's something strange happening that I don't quite understand. So the airway pressure has this little dip after about 1 second. I really couldn't figure out why this is. There is no maximum volume or anything that I adjusted here. Anyway, what you now see is that I increase my PEEP level to about 10 centimeters of water, and that allows the airway pressure to decrease more below PEEP, and that gives a little bit better tube compensation. Expiration not quite enough, and now I have a PEEP of 15 centimeters of water or millibar, and now we get the maximum tube compensation also in expiration. But as you can see, the tracheal pressure still deviates from our target pressure, the blue line, substantially, and the effective resistance is about 5.1 millibar per liter and seconds. Now compare this to my 3D printed self-made ATC ventilator. This is how ATC should really look like. A nearly constant tracheal pressure and a negligible added resistance of less than 2 millibar per liter and second. If you're not convinced by these measurements, do yourself a favor and breathe through a 7mm endotracheal tube connected to a commercial ventilator. Believe me, you will not tolerate this for very long, and neither will your patients.